digital neurology, we often use a sensor technology for digital neurology applications. And with these sensors, we can observe health parameters over an extended amount of time. A very simple health parameter would be gait velocity that we could observe using, let's say, a sensor at the patient's wrist over an extended amount of time. But we can think of much more advanced parameters that we could assess, including not only motor functions, but also cognitive functions, or even visual perception, sleep, mood, emotion, depression, and others. And in general, we can benefit from these assessments by allowing us to trigger patient-specific interventions on one side and as digital outcome measures for clinical studies on the other side. Think about sensor technology. We obviously can apply this technology to patients that are at home, and we can use on one side the well-known wearable sensors, Apple Watch and others, here a bit more sophisticated head-mounted EEG device for sleep research. On the other side, we can also use what we call ambient sensors or environmental sensors. These are sensors that are not directly connected to the patient, but are placed in the environment of the patient. So I have here a very simple example of a small sensor box that is placed in the apartment of these patients. And this sensor box is very simple. You basically have a peer sensor, that's a passive infrared sensor that measures human motion. You know these sensors, they turn on the light on public toilets. So very simple. But if you think of placing 10 of these sensor boxes and combining this with AI algorithms, you can look at the specific patterns of human activity and derive the activities of patients. And this then looks like this one here. So have a look at the left side. You see here recognized activities from an 83-year-old healthy woman. And you see on the x-axis 20 days, so day 1 to day 20. And you see on the y-axis the time of the day. So this would be midnight, 8 o'clock in the morning, lunchtime, 10 o'clock in the evening, and midnight. And you see color-coded the activities that were recognized at this very specific point in time. So sleeping in blue, cooking in red, eating violet, and watching TV in green. This is a pattern that you expect from a healthy older person. Here on the right side, you see the same pattern of an 83-year-old patient with Alzheimer's disease, here measured by the mini mental state evaluation. 16 points means quite heavily impaired, but this patient was still living by herself at home. And we expected, of course, to see these regularities dissolving to a certain point, but we were surprised in this study how strongly of the magnitude how this has been changed. So what I would like to take you from that is with ambient sensors, we can recognize activities of patients at home without needing to connect any sensors on the patient itself. Another type of sensor that we often like to use are, we call them object or object-attached sensors. And one example here is the tablet computer that we can also use as a type of sensor for both motor and cognitive function. So in this specific example, we have a gamified task that is presented to the patient. In this example is to connect dots, as you see here. Let's see. And to find the track that fits here. And what we can look at here is, of course, on the entire dynamics, so the timing, how fast this goes, then how the movement is exercised. You see here, for example, the difference how younger people, older adults, and Huntington patients solve the tasks. You see here the finger tracks on the screen, on this tablet screen, and you see the youngers, they are a bit sloppy in the corners. The olders, they do it very nicely, and Huntington patients, here you see some tremor effects. So what I would, another example here from a colleague in France. He used a paradigm where a task was presented on screen. It's basically this square here, and the patient needs to press the jump button in order to avoid oncoming objects. And they found similar results. They could predict the cognitive abilities of these, or some cognitive abilities of these patients using this app as a sensor. Another type of sensors that we often use are bed-attached sensors. You can imagine if you place here under the mattress a force sensor, you can measure on one side the movement of the patient in the bed, but you can also measure the beating heart. You can imagine the heart is basically a muscle, and when it contracts, this creates an impulse that can be measured down here. Same is true for respiration. So you see here just an example of such a movement pattern during the night. You see in yellow the bed exits, in orange you see tosses and turns, and you see how this evolves during the night. Here an example for the respiration rate that was measured during 1 year of a healthy subject, and here the same data of a 92-year-old patient with a developing heart insufficiency. I hope that I have convinced you that with these sensors you can collect behavioral and physiological data from the patients at home. The question is now, does this data relate to well-known or well-established clinical scores? And that is what we have looked at in this study here. So we asked ourselves whether the combination of ambient, variable, and object sensors can predict clinical assessments. For this study, the team looked at 45 participants, rather old participants, that were measured during 1 year of time. And the question was whether we could distinguish patients that were below or above a defined cutoff point in the domains fall risk, frailty, depression, and cognition. And if you look at the cognition result here measured as the MoCA score, you see that if you take the demographics by itself, so only the age as a predictor of cognitive performance, you are worse than if you would be guessing, okay? So we are below 0.5 on the receiver operating characteristics. However, if you take the sensor data, you get a very good, close to excellent discrimination between those above this threshold and those below the threshold. So what we take from that is that, yes, these sensors, they can be used to predict clinical assessments to a certain point, and they might give us clinically relevant information about our patients. However, there is a bit of problem. At home, in the patient's home, we are limited in the complexity of the sensor system that we can use for feasibility and cost reasons. And in the hospital, where we typically have a large number of sensors, we have the problem, or we are facing the problem, that our patients don't behave as they would behave in normal life. That's why we have implemented here at the Inselspital or at the SIGDEM the Neurotech Loft. The Neurotech Loft is an apartment with a bedroom, a kitchen, bedroom, kitchen, and living room. And patients can stay here for an extended amount of time. They can spend the night here, and we can observe their behavior while they are in this Neurotech Loft. And in this loft, obviously, we have a large number of sensors integrated. One of them is a camera system that is installed at the ceiling. And this camera system basically measures the position and orientation of the human body and overlies a 52-point kinematic skeleton model on the patient. What is nice about this approach that we don't need to fix any marker on the patient's body. What we also get are all information about interactions with doors, with drawers, and so on. When they do things in the kitchen, we see water consumption, power consumption, heart rate, respiration, and of course, during the night, we see, as I have presented before, movement, respiration, and so on. I always like to show this Neurotech Loft because it's not just something that has been developed for ourselves. It's really something that is offered as a service to the entire clinical research community here on campus. So we are always inviting other researchers to join us on using the loft for their own clinical studies, and we are more than happy to help others in doing so. But let's continue with what we are currently doing in this instrumented apartment. This instrumented apartment has been implemented to develop novel technology. I start with that. As an engineer, to conduct clinical studies and to optimize therapy. And the goal is, of course, to translate this technology into the hospital on one side and into the patient's home on the other side. And I would like to share with you two examples of current studies that are ongoing, one in the hospital and one in the patient's home. In this project on patient care in an old age psychiatry setting, we asked ourselves whether a digital care assistant could help nurses taking care of patients in an old age psychiatry setting. And the setting that we took for this study is the Station Baylor. It's located in the UPD Waldau, and it's a station or a ward with about 20 beds. You see here, these are the patient rooms, and you see here the Stationszimmer. And you can imagine that the nurse, especially during the night, travels around in these rooms to see where he or she is needed. Now, the hypothesis in this project is that if we would have a so-called digital care assistant that would use the sensor technology to recognize how patients are currently doing, this would simplify or facilitate the care of these patients. The idea is that the care assistance shows here in green the patients that are currently sleeping, in orange the patients that are not sleeping, like for example this patient here in room 12, he has pain and he is not calm. Then this patient in room number 3 is in orange. She is sitting on her bed and about to go to the toilet, which is not good because in this example, this patient is very prone to a fall. So how is this implemented? We have incorporated in such a patient room a bed sensor, as I have explained before, measuring movement and heart rate, respiration in the bed. You don't see the sensor, but trust me, it's down here. Then there is a LiDAR sensor under the bed measuring gait parameters and a radar sensor on the ceiling. You see it here. This one measures the movement of patients and also their position in the room. There is an interface to a nursing specialist giving them an overview of the different patients in the different room, indicating where they should go next. I have here some very first preliminary results. This is data that was collected in February, and you see that in this example, the system has created 1,500 alerts in these months. 1,000 alerts happened during the night and the other 500 during the day. And here you just see as an example the resolve duration. So you see that 60% of all requests were resolved within 1 minute. You see many or the large majority was resolved within 3 minutes. We are currently looking at whether this, let's say, this digital care assistant facilitates the care, especially during the night. Another example that I would like to share with you takes place in the patient's home. And here it's in the context of deep brain stimulation in Parkinson's disease. Here we are talking about severely affected Parkinson patients that have an implanted deep brain stimulator. Here you see how this looks like. We have 2 electrodes, and these electrodes, they are connected via this cable to the neurostimulator. The electrodes are typically placed in the thalamus, and typically we do bilateral stimulation. And the challenge here is that the control parameters of the stimulators, they have many degrees of freedom here. So you can select amplitude, frequency, shape of the stimulation, and so on. And it's not so easy to find the optimal stimulation parameter, especially since they are highly patient-specific. And very often the best stimulator for reducing motor symptoms does not reduce non-motor symptoms. That's why in this research project, we specifically focus on using these sensor methodologies to recognize symptoms. And we use speech measured by a microphone where we try to extract emotion. Also motor symptoms. You can imagine speech is highly sensitive to motor disturbances, but also activities and sleep, body movements, and computer game performance in order to estimate current cognitive abilities. A specific focus of this project is on emotion that is extracted from speech, because this is rather novel to the field. And here on the long term, we would like to use this information to better control the neurostimulator. So how do we do that? We use speech recordings. They are typically in Swiss Germans, so from the patients. So we typically ask them, how are you doing today? And we record their answers. Once the answers are recorded, we look at the answers, obviously, by transcribing them first in High German. This can be done automatically today. That works actually quite good. And then we analyze the content of the text. So what do they say? Do they say, oh, I feel very bad, I feel very good, today is a nice day, and so on? And we try to predict the current emotional moment of this person. On the other branch, we can also look at the acoustic features of their speech. So not really what they say, but how they say. Are the patients saying it with a happy voice or a very sad voice? And also on that branch, we can try to predict the emotion, the current emotion of the patient. And you can imagine if you combine the two, you might even increase the accuracy here. How does this look like in practice? So we have the implementation on a smartphone, and the smartphone typically asks questions like, how do you feel and what do you have planned for today? And then participants talk into the smartphone, and we use the microphone to record the audio file. And this audio file, as I've said before, is then transcribed to text on one side for the text-based mood estimation. And we also do the acoustic feature extraction for the voice-based mood estimation. Now, one of the challenges is, of course, to make sure that the patients really do this several times a day. And we have started having this app, showing them reminders, but this did not work that well. That's why we send today SMS reminders. We have realized that patients are our patients are very responsive to SMS. They receive the SMS, they press on this link, and then it automatically starts. I have here some preliminary results. This is still unpublished data that is based on 28 speech samples. All participants were talking Swiss German, and the speech samples are from 7 patients with Parkinson's disease. The results that I'm showing here are only on the text-based mood estimation. Now, what we asked patients, we asked them to not only record their voice, but also tell us how they currently feel. And you see the patient-reported feelings on this side here. So here they feel positive, here they feel neutral, and here rather negative. And you see on this axis here the AI prediction, and you see this is the region where you want to be. So you see 85% of when patient reported positive were recognized as positive, and 100% of all negatives were also rated as negative. The algorithm currently still has some challenges in the neutral in order to distinguish the two. So I hope that I have convinced you that we can use this sensor on one side in the hospital as well in the patient's home. I have shown you this example of the deep brain stimulation in Parkinson's disease. Currently, we have another project ongoing where we use these methods to better understand fatigue in MS. This is a very good use case for these methods because also fatigue fluctuates and needs to be observed over an extended amount of time. So if I come to the conclusions, we see that we can use these methods in patients at home, in the Neurotech Loft, as well as in the hospital. And I have introduced wearable sensors, object-attached sensors, ambient sensors, and last but not least, the speech recordings, which we believe has a great potential because it can be easily scaled to other patient populations, and we can also scale it to large patient samples. And I have introduced algorithms that produce digital biomarkers down here. I believe that the sensors recordings, they really can be used to collect additional data on everyday behavior in order to supplement clinical measurements. The areas and the domains are much more than just motor functions. It can be also cognition, sleep, mood, and depressions. In general, we find very high acceptance among patients, but rather low among healthy test subjects. Healthy test subjects, they often don't like these sensors too much. I have mentioned that the Neurotech Loft is here as a service, and we are welcoming research projects from clinical research groups around the Bern ecosystem. And with this, I would like to advertise the annual meeting of the Clinical Neuroscience Bern that takes place in September 6, and I would like to thank you for your kind attention.